All right, so welcome to Synchronous Motors. And what we're trying to do with this particular lab is we're trying to see how any synchronous machine, or induction machine for that matter, can be specifically synchronous, how we can have a synchronous machine become a motor or a generator. And last week, if you remember, we actually had a prime mover and we operated this as a synchronous generator. So the prime mover was the synchronous was the in this case it was the power supply or the mechanical power supply is a better way to say it. In this case, we're going to actually have we're going to actually have this the opposite direction, which is we're going to be driving the 4-quadrant dynamometer power supply with the synchronous motor. So the output last week was electrical power and the input power was torque. We're flipping it around this week. The input power is electrical power and the output is torque. So what we want to do is, remember, we have to flip the screens down, or the panels down, so we can go ahead and connect our two devices. And this is the mechanical coupling that we're going to have. And we'll raise the front panel, raise the front panel. Now we're going to go ahead and energize a synchronous motor. And if you remember last week when we did lab, we didn't have any AC connections from the synchronous motor from the power supply to the synchronous motor because we didn't need it. It wasn't necessary. And in this case, we actually do need to do that. So we're going to go ahead and run our power to our synchronous machine. And now, because we've coupled it to here, we actually have the capability of monitoring or powering this up. So let me just make sure we have torque, and we don't actually have to do the power connections. Okay, all right. So we have the power now, but the problem is that these windings here on the synchronous machine are completely independent from each other. You can see electrically, nothing can go from the winding that's between terminals 1 and 4 and 2 and 5 or 3 and 6 until we connect them. So we're going to go ahead and connect these in a Y configuration. And we have our machine basically ready to go ahead and get power. Now, we want to make sure that we can understand how to use this dynamometer, because we want to go ahead and set it as a brake. So we're going to flip the switch. We're going to bring up the 4-quadrant dynamometer. And in this case, it's going to be operating as a brake. So we're going to move this as a prime mover brake. And it's not going to be constant speed because we're going to require the synchronous machine to go ahead and do that. So we'll click the prime mover brake. And why is this doing speed control? Okay, well, let's just set it as it's like all of a sudden my function settings are just gone. So let me go ahead and try to enable that again. Okay, so we're going to set it up as a 2-quadrant constant torque brake, and then we can adjust the torque demanded here. So we'll minimize that for the time being. And now we're going to turn this unit on, and we're going to turn up the voltage, and we should start to see rotation. And hopefully you can see, let me see if I can lower the front panel, but you can actually see that this is rotating in the clockwise direction. So both the motor is actually driving the mechanical power, but the dynamometer is operating in the direction, okay? So we're feeling pretty good about the rotation because we want to go ahead and make sure that it rotates in the clockwise direction. Now I'm going to raise the panel, and I'm going to shut the power supply off, and I'll just stop the motor, make sure it doesn't continue on. And now I'm going to go ahead and run a field current into here, okay? So there's a couple options I can do for this part of the lab. It's just as easy to go ahead and take our fixed value here, so our fixed DC, and then run it into here. Now, the question I have to start off is, because I powered this up now, this is provided with 120 volt DC and it's fixed 120 volt DC, so it doesn't matter what's happening here. Does it make a difference, the amount of field current that I provide here? Does it have any impact whatsoever in terms of the operation of the motor? Before I had no connection, now I have a connection. Is there any change? Well, there isn't any change, right? Because before the switch was operating in an open circuit or open configuration. So no, there is no change between the two. Okay. So what we want to do is we want to recognize that just by connecting this DC has zero impact on this particular device unless the switch is closed. So we're going to keep it open for the time being. Now I'm going to go ahead and set up my DAC. And I'm going to run the torque output. And if you look here, hard to see what there's zooming quite a bit, but there's the torque. Oh, here's the torque, sorry. So I'm going to run that to channel 7. And then I'm also going to run my analog input over here. So now in my metering window, I can actually display the torque. On. And this is where you have to read the steps about the corrected or non-corrected. If you look at the particular steps, it tells you what condition is what we want. So non-connected and connected. In the non-corrected mode, the torque by the torque measurement mechanism is calculating this torque. The corrected mode is corrected by compensating errors. The corrected torque is what we want to use. So we want this to be corrected. And now we can go ahead and turn on our power supply and get this thing spinning. And now we can bring up our torque, turn it refreshing. And you can see that it takes about 0.265 Newton meters to go ahead and get this to rotate. Now we can go ahead and start to increase it. So you can actually change by rotating this, and you'll actually see now, should be able to see that it actually has more torque. Why isn't that outputting more torque? I guess it ignores that button unless we enter it over here. Okay, so now we're entering it. I guess I had to have the thing turned on. And you can see I can go ahead and turn this up. So what we want to do is we want to set this as maximum, and it would probably be easier just to go ahead and set that as high as it possibly can. I think you can go all the way up to 3 Newton meters. So we'll specify the 3 Newton meters and then see if this machine is able to do it. So you can see that the machine is running, but it looks like the speed is a little bit off. So let's go ahead and actually let's monitor our speed. We'll monitor that parameter, turn this on. So it's not at 1800 RPM, which this machine should operate at. If we go back in here and we change this to 0, our speed should go up to 1800 RPM. Why is it not going up to 1800 RPM? Does anybody want to guess? You can see there's very little torque, and this motor is capable of putting out 175 watts at 1800 RPM. And if you recall, a synchronous machine is one where it must operate at synchronous speed. Synchronous speed for a 4-pole machine should be 1800 RPM. This is only running at 1748 RPM. So does anybody have any issues with this, that this is doing this? Clearly it's not 1800. Why is it not 1800? Did I pick on anybody? Well, it's kind of a subtle thing, but the reason why this is operating this way, and it's very interesting, But this switch is open. So we've already said that there's no DC current going in here. And if you remember, for a synchronous machine, you have to have a DC current going on the field to actually get this unit to rotate. But in this case, it's still rotating even though this is open, right? The switch is off. There's no DC going in here. So if you recall, when we discuss synchronous machines, you have up to three sets of windings. You have the stator winding, which is where the AC three-phase power comes from or gets supplied to. You have the field winding, which is the one that rotates around and you provide DC. But we also talked about a set of what are called damper windings. And damper windings are those that actually operate very similarly to an induction machine. It's essentially a squirrel cage bar around the rotor, and it allows for current to flow so that if you get any changes in your machine, it'll smooth out the operation. So that's why they're called damper windings, because they damper out any changes. And if you notice, when I flip this switch into the on position, you'll see very quickly the speed will go to 1800 RPM. There you go. So when it's open, it operates as an induction machine. When it's closed, it operates as a synchronous machine. And so when you're doing steps 5 and 6, when you look at the starting torque and all that stuff, what you need to think about a little bit, because right now you can see that I've set this as a minimum, but the torque went up. But look what happens when I crank this up. Nothing happens in the exciter, right? So no happening there. But let's go back over here and let's see if I can turn my knob up. And so now I'm going to rotate my knob. I wish the speed was increasing to make it easier to see what's going on, but let's bring up the metering one. So we're still at 1800 RPM, and I continue to increase, keep cranking it up. And you just have to go through the process, but it's still able to maintain a fairly constant. Is this not refreshing? Because this seems like it's not refreshing, because the torque here. Oh, is this stopped? Yeah, okay. I'm not sure why it didn't go that way, but you can see now the RPM is correct. Let's change this back to an analog one. There we go. You can see that that's too low. So this is way too much torque that's being demanded. So if I back this off, let's start it over here. Not able to pick up speed. Dial it down. Still not able to pick up speed. Trip offline. Oh, it still seems to be okay, but for some reason it is unable to go up to speed. So why isn't it up to speed? Interesting. This is only drawing this, but for some reason it's not able to do that. So let's toggle a switch. Oh, the voltage got changed. I'm sorry. Sorry about this, folks. I'm not sure why it's not rotated. No torque here. Nothing tripped. It's like there's no power connection. Let me try going directly across the line. This shouldn't make a difference. I wonder if the software is glitching perhaps, because at this point, we should be able to get this unit rotating. Maybe it's just a graphics thing. Well, I am perplexed. Put the power supply here, but I don't believe it actually needs the power supply. All right, so now I'm starting it as an induction machine, so you can see how it's increasing its value. So what is my speed? So 1749. Then I click the switch and I get 1800 RPM. Okay, so it must have been that the torque that was demanded was too low. So essentially what I was saying is you have a starting torque. And let's see. So the starting torque, we want to make sure, set the exciter switch to the closed position. So let's flip the breaker, set it in the closed position, and set the exciter switch and turn the knob fully clockwise. So we want the minimum amount of current to do it. And so now what we're going to do is we're going to go ahead and see if this unit is able to go ahead. So now you can click the switch, and it doesn't matter now because this is going to go right to full voltage. So I'm going to bring up my metering, toggle the switch, and it's not spinning. That's because this is too much. So let's turn this down. This is really acting strange. It is not, whenever this is closed, it doesn't want to seem to be able to operate correctly. So that's the torque, but it doesn't seem to be able to start. Sure why. This should be able to start when the machine. Oh, okay. Let's do it again. Let's turn this off. We've got this at minimum. We'll start over here and we'll see if we turn the voltage up this way, it's able to do it. So let's stop the motor. Okay. Well, I am not sure what's going on because it is unable to start rotating when you have the switch in the on position, and this is at its minimum. So I know the voltage is 120 volts. That's what we indicate here.
Paul, change your status to started. I think that's what I kind of did. Maybe that'll help. I'm not too sure.
Yeah, I don't get any change. Is anybody else, are they able to get it to a function? Because I am not able to do that. I mean, I use a slightly different unit than in lab, but I was able to get it to work, and now it does not seem to be. Let's, I want to do constant torque. Is anybody else able to get it? It sounds like if you switch that, I don't know if I need to restart LV sim, if it's a glitch in it, because we did slightly different configuration in lab, but this just does not seem to be able to get it to rotate when it's a synchronous machine. But we were able to do that during lab today, where if we ran it over here, we were in fact able to get the unit to run, especially if we increase the voltage slowly or relatively slowly. Once we got to about here, it was able to do it. And I'm not exactly sure why this does not want to be able to rotate. Yeah, I don't know. I'm sorry. Maybe you cannot do part 5. Is anybody able to get part 5? Because when I did it at home, I was able to get 0.6 Newton meters of torque for the starting torque.
Oh, I guess I'm just wondering how we get the starting torque, what we'd have to have the brake set at.
You
get
shouldn't
that.
need to have the brake set up anything. You should be able to get this to start up, and you just when you see it actually start to rotate, you actually start to see that's what the startup torque is. So if I flip the switch over here, there's no load on this, and this is the startup torque. And I think, let's see. Yeah, so hold on, let me turn this off. If we use the same lab setup that we had today, I don't know if we can actually do the dynamometers that we have. When we have in
Hey,
lab.
Paul,
Yeah,
I just flicked my exciter switch on and off,
yeah.
and for some reason mine worked after that.
Well, that is going to be the case. It's going to work as it gets up to speed. So let me do this. I'm going to stop this. I'm going to delete this module, and I'm going to put in a more basic prime mover module. And just give me 1 minute. You don't have to change your circuits. Just let me try. Let's see if I can change it. So this is work. I have to run my low power output from here to here. And I gotta run my analog here. Okay, so now I have that. And this is going to be operating as a dynamometer. So the switch is closed. This is at its minimum. Flip the switch. Start to rotate it. And then, oh, I'm sorry. I didn't actually, forgot to couple these together. Oh. It does not want to rotate. It rotates here. They must have made a software update because we used to be able to do it and it would work. So it doesn't look like we're going to be able to do this one because now they're treating it like it's a synchronous motor that you can actually, even though during lab today, physical lab, we were actually in fact able to do that. So just say unavailable for step number 5 for your starting torque. You were unable to do that. And then for the synchronous generator in the open position, which we have it now, you can try that test again. Let's see, I'll shrink this a little bit. And then I'll bring up the meter window so we can see. So I'm going to stop this. And then I'm going to see if I can see what the starting torque is. I might not be able to record it. Flip the switch. Yeah, so the starting torque, the maximum it can get to is 0.33. But this is where what I want to do is I want to actually maximize what this value is. And so this is the actual maximum torque. Now you can see that it's actually stopped. So this is the actual peak torque that it's able to produce. This is the max starting torque. You can see the speed's low, so you can get about 2.1716 RPM. So that's, or I'm sorry, Newton meters, and that would be the corrected value. If you go to the non-corrected value, that includes the actual, includes different, it includes the bearing and losses and the mechanical losses in the system. All right, so that's up to step 6. Now you can go ahead and you can see what the stabilization speed is. So in this mode, all you're going to do is bring this down to its minimum value. And you should see that this, because our switch here is open, it's going to operate exactly like an induction machine. Okay, so this operates as an induction machine. Once we're up to speed, we flip the switch, and now we go to synchronous speed. So that's parts 7 and 8. And so now you'll go ahead and you'll do steps 8, 9, 10. Let's see and check. So 8 and 9 should be pretty quick. Now what you're going to do, though, is you're going to go ahead and you're going to change your resistor value. So let's stop this. And now this is when you're going to have to go ahead in and change. You're going to have to add some resistors in here for your field current. So I'm going to delete this wire here, delete this wire here. And now I'm going to run through my parallel set of resistors. Run those over here. And then back over here. And so this is going to allow you to vary your resistance so that you can get from 100 to 800 milliamps. And this is important for you because you're going to try to develop a set of V curves for your machine, which actually shows you as you vary the excitation, you're going to start to see that the reactive power goes down and up, essentially. So you're going to actually, it's actually the line current, it's actually going to vary down and up. And so that's the process you'll do it. You may have to put a jumper in some of these, so you might have to drag these and bypass some of these resistors, but you should be able to do 100 to 800 milliamps to do steps 9, and then 10, 11, 12, all those should be just answering the questions with a specific current. So sorry we were not able to get the starting torque. I don't know exactly why, but I've got you to this point. So I should have hopefully understand to the point where we're ready to start on procedure step 7 and proceed from there. So any questions before I give you the time to work on this? TJ, you were able to get it working the original way. Yeah, but like I said, it's not working exactly. So this one works fine. It's dynamometer. As long as you get this set in dynamometer, it works really well. The other one is just being more specific. So we'll just use a simpler basic one. This is very similar to what we had in lab today. And it seems to be working relatively fine, except for the synchronous machine will not start unless you have it in there. So you can just put NA for step number 5. You can just put the start torque as NA or something equal to 2. So any questions? Okay, I'm going to pause the recording. I'll stop sharing and feel free to ask questions away. So stop sharing.